Hi, I'm Gary, and I want to show you how I use Cloudy. We're not going to talk about Cloudy today. We're going to talk about spectroscopy and how we do spectroscopy. So you can skip this if you're comfortable with that. We'll talk about using Cloudy to do spectroscopy next time. This is the ultraviolet optical near-infrared spectrum of the Orion Nebula. So this shows a conventional way of producing spectra. We have the wavelength in angstroms across the bottom and some measure of the intensity of the spectrum at various wavelengths. So we see several strong lines. The strongest line is this O3 notation, and we have lots of other lines in the spectrum. This is the brightest lines there. If you go with a really big telescope like the VLT, get a long exposure, you can get a really good spectrum of the Orion Nebula. So this paper in 2004 did that with a good hard look with a big telescope at a naked eye object. And so the table here shows the conventional way astronomers report spectroscopy. So the leftmost column is the wavelength in angstroms and measured in the telescope. The middle column there, one column over, so it shows something that a bit confusing at first. Clearly, there's a lot of element names. From the top, I see silicon, iron, oxygen, back and forth. Next, there are these brackets that come and go. We don't use those in Cloudy, but it's interesting physics behind them. And lastly, you'll notice Roman numerals. How often do you bump into that? So Roman numeral 2, Roman numeral 1, Roman numeral 3. So this has to do with a mistake that was made in the 19th century. They didn't know about the electron yet. And so as atoms became ionized, they started counting from 1, 2, and 3. So 1 is atomic, is no electrons removed. 2 would have one electron moved, so it's off by 1. There's other designations here, a lot of information that's available in the spectrum. This is the other way of plotting this information. This is an energy level diagram, sometimes called a Grotrian diagram. So this shows a number of different species, one electron hydrogen, is ordered by increasing number of electrons. And then we see iron 2 is over here on the far right. This the marks here, horizontal lines, are the energy levels for the electrons. So an electron would normally be in the ground state, the lowest possible level, and you can put an electron up into one of these excited states, they're called. It will linger up there for a tiny bit of time and then spontaneously fall back to eventually get to the ground state. So that produces the emission lines that we just saw. This plot is calibrated so that all these different elements have what's called the same ionization potential, relative ionization potential. So the ionization potential is the energy required to take an electron that's bound to the ion and remove it, take it off to infinity. And they all have different ionization potentials, but we've normalized it so that the top is 1 so we can compare them. This red band at the top is not a bound level. So those are called continuum electrons. So an electron can be in one of these bound levels, or it can be up in the continuum, just floating around in the gas. The next things to notice are the 0 to 1. This is the energy of these different levels divided by the ionization limit. So 0 is called the ground state. Most electrons are going to be found very close to the ground state down here at the bottom. These other levels are excited states. And then 1.0 on this is the ionization limit. So you put an electron up there, there's barely enough energy to hold on to the atom. And just slightly more energy, it goes up into the red hash area. It's no longer bound to the atom, but becomes part of the continuum. There's two simple cases, and they provide rules of thumb, although it's actually more complex than I'm about to say. In the few electron case, that means hydrogen has one electron. Carbon has three. Uh, so these are the number of electrons is increasing. What you see is that very few electron systems tend to have their states very up high, whereas as the number of electrons increases, the number of lower states increases. So for 1 and 2 electron systems, so this would be like hydrogen 1, helium 1, helium 2, the levels are going to be very, very close to the top of the atom up near the continuum. And so these levels, if you see, say, H beta is this transition from here to here. It's pretty high up level. It's better coupled to the continuum up here than it is to the ground way down there. So these levels up here tend to be populated from the continuum. They produce what's called a recombination line. When you get to many electron systems, for quantum mechanics, it's more complicated because the orbiting electrons interact one with the other. And what comes of that is there are many states that are possible. So you see this very, very dense matrix of states. Most bound electrons are in the ground state or close to it. The free electrons in the plasma have a certain kinetic energy. It's determined by the temperature. And for typical photonization cases, this vertical bar shows the kinds of energies, that's KT, the Maxwellian energy. And so if you have an electron in a ground state, and if there are free electrons with sort of this much energy, they can collide with the ground state and excite it to one of these levels. So these levels down towards the bottom tend to form by what's called electron impact excitation. Electron hits the ion, gives the electron gives its kinetic energy to the ion. That energy is used to move the orbiting electron up, and then later on emits a photon. That's said to be cooling the gas because kinetic energy was used to promote the electron. Then it makes light that freely escapes. I'm not going to go into this. It's in Osterbrock. There are bootleg copies of Osterbrock in the docs folder. Uh, Nice, beautiful physics. It's fun to think about it. The practical problem you'll have if you have an interesting spectrum is there's going to be a lot of lines, and you have to figure out what they are. There's two places to go for astronomy. Peter van Hoff has a line list that's at this site in which you tell the program, I found a line between this wavelength and this wavelength. What could it be? The code will search databases and find all the possible lines that are in there. It may come up with several lines. Emily is a code that originally was developed in Space Telescope, but it tries to use machine logic to try to figure out what lines are in your spectrum. In this case, for Emily, you would give it the entire spectrum. And if it finds a lot of iron 2 lines, when it finds another line it's looking for, it would guess first, maybe it's iron 2. So it does a lot of rules of thumb and guesses trying to figure out what's in your spectrum. So it's getting something of a following. The authors have continued developing the code, and Emily was the first version. You go to their paper, I'm sure you'll find more recent updates. The gold standard here is the National Institute of Standards and Technology. This is their web form that shows you access to their tables of energy levels and also of emission lines. If we stick with O3, the strongest lines in an H2 region, and query NIST about O3, so this is their query form, and if you hit send, and focusing now on the region in the green part of the spectrum, and so it gives a lot of summary information, but it found three lines, three possible lines around where the O3 line is. And two of these are the strong O3 optical collision excited lines. So this is two ways of presenting emission lines. So on the left is a screenshot from the NIST table of the lowest levels in O3 or O double plus. So this is the ground state here. This is the energy level energy counting from zero. It's a unit called a wave number, which is uh, the most common unit of energy in actual spectroscopy. So these three levels are very, very close to the ground state. This is the ground state. This is the other way of representing this. So we have, it's not drawn to scale, but here's those three levels are down here. These make the very famous 52 and 88 micron line in mid-IR. Next level up is this one, shown here schematically. And this level cascading down here make the two very strongest lines. Then up one more is 1S, sky way up here. And this makes very faint lines, which can be used to measure temperature. So this is important spectroscopic diagnostics. This is slightly opposite in that the tables have zero at the top for the very top row, and zero represented as energy levels is going to be at the very bottom. We won't go into selection rules. We're going to just use some databases and look at this for some practical spectroscopy. But AGN3 does have two appendices that goes into atomic physics. Then lastly, let's think about a nasty habit astronomers have in mixing up species and spectra. They're not the same, and you can get into trouble with it. So H naught, C3 plus, O2 plus, H2 and HCO, they're baryons. That's matter, it's mass. This other notation we've seen, H1 carbon 4O3, that's a spectroscopy notation that indicates a collection of photons that was detected. This notation has to do with some misconceptions they had in the 19th century. Cloudy doesn't use Roman numeral. Its C++ standard library doesn't do Roman numerals, near as we can tell. We'll talk about how Cloudy does deal with the Roman numerals. But the thing to remember is that you can't swap one for the other unambiguously. If you're looking at, say, the Lyman alpha emission line, it can be produced. That's a line from the n equals 2 excited state. That's three-quarters of the way up to the top. It can be produced by recombination from H plus in an H2 region. That's how it forms. It can also be produced by impact excitation from the ground state. And so it can be a collisionally excited line and it can be a recombination line. And quasars are mainly collisionally excited. So emission is ambiguous. Absorption is not ambiguous. If you see a Lyman alpha absorption line, you know that the photon was absorbed by a hydrogen atom in the 1s level. And so it can only be produced by atomic hydrogen because it needs to be there. So absorption is unambiguous. It can trace atomic hydrogen. Emission, if you see an emission line, it could tell you there's H plus there or there's H not there. So what we're going to do now, next time is in the next video, go and use Cloudy to look at some of these quantities and see how the spectrum varies when we change some physical parameters. See you then.